Hi folks, we're talking about tutorial problem number 21 from chapter 12, and it reads, the axle in the figure is half the distance from the center of the rim. So this black dot is our axle here in our picture, right? So we're assuming that it's half the distance from the center, so we know the diameter is 30 centimeters. Radius would be 15 centimeters. So this thing is 7.5 centimeters from the rim. So our first question is, where is the mass, the center of mass of the disk? So we're assuming that this disk is uniform in mass distribution. We have no reason to assume otherwise. So as long as your object has high symmetry, which a circle, a disk does, we would assume not only high symmetry but also a uniform mass distribution. Your center of mass is going to be just straight in the center of the disk in this case, right? So the center of mass is in the center of the disk, assuming uniform mass distribution. So we are not we're not biasing. We're not saying one side is heavier than the other. And so this is going to help us place our torques when we think about the total torques on our system. We always want to put the weight of an object at its center of mass. So draw F and R for each torque on the system. Let's just draw a replica of the system here. And we're going to have 3 torques, right? But they're all relative to our pivot, to our axle, right? I have my center of mass here. So I have R1, which is going to be our weight. And then I have F1, which is our weight, right? R1 is to the pivot to our center of mass to our weight. R2 then is going to be all the way to the right edge because I have this mass hanging off of it. And the tension is going to be applied right where the rope starts to last have contact with my disc, which is right on the edge here. So I have F2, and then finally I have F3, or R3 first, and then F3 for the other tension. Right. So if I'm just kind of labeling all of these things, I can say that F1, just to remind myself, this thing has 5 kilograms of mass. And so I'm going to have 5 kilograms times 9.8 meters per second squared. F2 is going to be 10 kilograms of mass hanging off this thing, 9.8 meters per second squared. F3 is 15 kilograms, 9.8 meters per second squared. R1 is from here to here, right? So we're probably thinking the 7.5 centimeters. R2 would be 30 centimeters minus 7.5, so what, that's 22.5 centimeters, and R3 would again be 7.5 centimeters. That looks pretty good. Label which torques are positive, which try to spin the system counterclockwise, negative, try to spin the system clockwise. So again, we are rotating about this axle. Torque 1, is applied right here, and we see that it's on the right hand side of my axle and it's pointing down, so it would spin the system. Let's move to a different color. It would spin the system this way, right, which is clockwise. So torque 1 is negative, right, clockwise. Torque 2, similar. Torque 2 provides a similar thing, right? So torque 2, I'll just write in red. Torque 2 is also negative, again, because we're going clockwise. Finally, torque 3. Torque 3 is on the left-hand side of my axle and pointing down, so it's going to try to rotate in the opposite direction, in the counterclockwise direction. So torque 3 is actually positive. And we can also talk about the directions of these torques based on this clockwise counterclockwise thing. If you wrap your fingers, not your thumb, but your fingers in the direction that the torque is trying to spin the system, so in the case of torques 1 and 2, you're wrapping your fingers clockwise, you find that your thumb actually points into the page. That's the direction that the torque actually is. That's the direction of the torque vector. For torque 3, if you wrap your fingers in the counterclockwise direction, your thumb points out of the page. And again, that is the direction of the torque vector. So what is the net torque on this system? The net torque is equal to the sum of all the individual torques, right? So I'm going to have torque, let's say torque 3 minus torque 1 minus torque 2. The reason I put torque 3 first is because it's positive, right? And I like to generally have positive things out front. That's just the way I do it. So if I'm thinking about this, I'm going to have R 0.7, no, 0.075 meters times 15 kilograms times 9.8 meters per second squared times sine of 90 degrees. It's actually something that we didn't talk about here. All our torques, we're thinking about R cross F, right, for our torque. And we can simplify and say that, you know, the magnitude of our torque is equal to R F times sine of the angle between them. Well, the sine of the angle between them, if we extend all these R vectors out, is 90 degrees. So all of these torques have a sine of 90 attached to them, but sine of 90 is 1. So I'm going to include them just for I don't know, trying to be as explicit as possible. Please understand that sometimes I might drop them, and it's just assumed that the sine of 90 is 1. All right. So we have our third torque here. Let's just kind of stack these on top of each other. Minus 0.225 meters. I think I'm doing torque 2 next. Let's do torque 1 like I have it in my picture here. 0.075 meters. I have 5 kilograms times 9.8 meters per second squared times sine of 90 degrees. And then finally, minus 0.225 meters times 10 kilograms times 9.8 meters per second squared, and then finally, last sine of 90 degrees. When I plug this into a calculator, what do I get? I get a net torque equal to negative 14.7 Newton meters. All right. So the negative torques win. We start to feel an angular acceleration that will make this thing spin, in the clockwise direction. And again, I want to highlight the unit of torque is Newton meters. That looks like a joule, but do not put joules. I will take off points if you put joules. All right, this is not an energy. This is a Newton meter. All right. Let's go to the next page. Next page, which direction does the torque vector point? So we just kind of talked about this a little bit with how the torque wants to make the, tries to make the system move counterclockwise versus clockwise. You spin your fingers in that direction, and the way your thumb points shows the direction of the torque vector. You could also do a more strict right-hand rule of fingers in the R direction. You bend them into the F direction, and your thumb points in the torque direction. That works as well. Since F1, since torque 1 and torque 2 are negative, we can use those as kind of the basis of our net torque vector. And if we did that, we would find that we have a torque going in to the page, right? And that's the exact same result that we found if we curled our fingers in the clockwise direction. We would find that our thumb points into the page. So in any case, the direction of the torque vector points into the page, or into the screen if you're just watching this. The moment of inertia for a disk through its center is 1/2 mr squared. Use the parallel axis theorem to find the moment of inertia with the axle set where it is in this problem. So parallel axis theorem, if we remember back, says that I can find the moment of inertia anywhere about any point on my system if I know the moment of inertia through the center of mass, and I add the total mass of my object times the distance squared from the center of mass to the new pivot point. So in this case, right, let's make that a nice circle. My center of mass is here, my pivot point is here. What is D? D ends up being 0.075 meters. So I have 1/2, or another way that we could say that is R over 2, the radius of this thing over 2. So I have 1/2 mr squared plus m r over 2 quantity squared. That's what we just said D was. So that ends up being 1/2 mr squared plus 1/4 mr squared. I can say that that is 3/4 mr squared. If I plug in numbers, I'm going to skip writing out all the numbers on this one, but if I plug in numbers, I find that I get 0.084 kilogram meters squared. All right. So that's plugging in 5 kilograms and 15 centimeters, or 0.15 meters in for R. Finally, what is the instantaneous angular acceleration right as the system is let go from rest? So if I'm thinking about the instantaneous angular acceleration, if I think about all the pieces I have at this point, I have something like this rotational force, I have torque, I have this thing like rotational mass, this moment of inertia. I'm trying to find this angular acceleration, right? So if I think about this, I think I have all the pieces to say, instead of F equals ma, I have torque equals I alpha. So if I plug in some numbers, I have negative 14.7 Newton meters over my 0.084 kilogram meters squared. What do I get for alpha? I get alpha equals negative 175 radians per second squared. And then this negative, right, the negative indicates that we are moving clockwise. right? That we have clockwise motion. So that's the problem. That I'm trying to break these problems apart a little bit more and ask intermediate steps, just so we're seeing how all the pieces kind of fit together. Right? The parallel axis theorem seems a little bit, the first time that we go through, it seems a little bit like, why are we doing this? But it's actually really convenient when we don't have an axle or a pivot point exactly at the center of mass. So this is a pretty straightforward problem, I think, but it's a really good practice problem to get used to torques and how forces and radii kind of work together in this. If you have questions, shoot me an email or see me in office hours. Other than that, I'll see you in the next video.